Welcome again, my dear students. In the last class, we discussed the uh, Cayley theorems. We provide a proof of a Cayley theorem. One corollary about the Cayley theorem is saying that this means every finite group G is isomorphic to some permutation group of Sn. And then we discuss some example for order 3 and order 4, and we show that satisfy this condition. We can easily find the some isomer subgroup of a isomorphic, which is our isomorphic to some permutation subgroup of order Sn. So this is today lecture. We start with the direct product, and the last topic of our series of lectures. And in this lecture, we have to uh, discuss the two types of a product. One is external direct product, another is a internal direct product. So let's start today lecture with the external direct product. Means we have to direct product take a if we take two groups G and G1, and then we write a element of these two product, we take a direct Cartesian product of these two groups, and then under the binary operation of this G1 and G2, this Cartesian product again form a group, and that group is called is a external direct product. So I just said that if we have a G under the binary operation uh, dot O, and this is G1 is a O are two groups, then we make a Cartesian product of a G and G1 into a new group structure. As said, our group is just is an ordered pair X and Y, G cross G1, because you know that the order elements of a G cross G1, where X is the element of a G and Y is the element of a G1. So we define a binary operation, the diamond on G cross G1. So we have to take this X1, Y1 are the element of this G1, G cross G1. X2, Y2 are the elements of also this element. Then we have to take a binary operation, and then we have to define is this. And now you see we have two different binary operations. One is for this G, and this is for G1. And now X1, X2 are the element of a G, and Y1, Y2 are the element of a G1. So this means we have to take X1 and X2 is by the operation of this binary operation of a G, and because Y1 and Y2 are the elements of this G1, so that means in this case we can say that this binary operation is the operation of what is the binary operation we have to take in for G1. So if we can define a binary operation G1 G cross G1 into this form, that is just a multiplying element in the first coordinate as we do in G, and the element in the second coordinate as we do in G1. So just we take a composition of a first component is a elements of a G, and the second binary operation component of a elements of a G1. So we have two different groups are there. So now we from this we can try to under these binary operation, this G cross G1 we have is a group or not. We have to just say that. So let G and G be a two groups. The set G1 under this operation. So we just say that under this binary operation, this is a group. So now first we have a G is a group and G2 G1 is a group, and where this X1 and X2 are the elements of a G, then we by the this means X composition, X1 composition, X2 is also the element of a G, and also you have a Y1 and Y2 are the element of a G1, then Y1 circle Y2O is also the element of a G. That means G1, and this is the element of a G, and this is the element of a G1. Then this clearly this is the element of a G, and this is the element of a G1. That is this complete element of a this nothing but is equal to G cross G1. And if this is the element of a G cross G1, that means this can we can say that this binary operation X1 Y1 diamond, we can say that this is equal to diamond. We have to just say that okay, this diamond if x2 y2, and this is also the element of a g cross g1. And if g cross g1, then the first condition of the our group for a closeness is satisfied. So if it's closed binary operation, this diamond is closed for this thing. Now we have to try to because first we check the product is closed, and this is clearly we have a I just said that this is the element of a G, this is the element of a G1, so this means clearly this is satisfy this thing. Now we have to try to take a associativity, and now if associative means you have to just take a x1, this is we have to define into this form. You just check x1 y1, then you have to just take a x1 y1 diamond of I take a just we have a x2 y2, and then we have a diamond of, okay, just take a these two, and then we have a x3 y3. Now if you just check, if this can be written as a x1 this dot o x2, and then you have a y1, and circle you have a y2, and then you have a diamond of x3 and y3. And now this can be written as the form of this again by the definition of a binary operation. This can be written as a x1 o x2, and then dot o is equal to x3, and then this can be written as a y1 circle y2, and then you have a circle of a y3. Now you know that this x1 x2 x3 are G, y1 y2 y3 are G, that way they are clearly is a associative. So now we're using the associativity of a G and G1 here. This can be written as a x1 dot of a x2 dot o x3, and then can be written as y1 circle is equal to y1 y2 circle y3, and this can be written as the same as a, again by the definition of a this x1 y1, and you have a diamond of, you have a x2 dot o x3, and then you have a y2 dot o y3. And now this can be again we using into the form, you have a clearly x1, you have a, and now you have a y1, and this is equal to, you have a diamond, and then this can be written in the form of a, you have a simply again the product of this can be written as x2 and y2, and this is equal to diamond of x3 and y3. And now this is nothing but is equal to, we have to write in the form of this form. So this can be starting this form, this can be written in the form x1 x2 in this form this. So this means clearly we say that the product we have to define is satisfy the associativity condition also. So this means clearly I just say that it's also the associative is there. Now we try to, there's this existence of a identity. So we assuming that E G and EG1, EG is the identity of a G, and EG1 is the identity of a EG is the identity of a this, EG1 are identity of a G1, then X is the element of I, G and Y are the element of a G2, and then just we take some elements of a X and Y, and then we have to take a direct product of this some EG and EI, and then we can simply say that suppose X, Y diamond of a EG and EG1. Now by the definition this is X circle EG, X dot circle is EG, Y circle EG, and now because you have a X is the element of a G, and X G sorry this EG is the element of a identity element of a this G. This means X is the binary operation is this EG is equal to, you have a giving X is the same as a EG, and then is equal to X. So this means this is provide you a X. Similarly EG1 is the element, EG1 is the identity element of a G2. So you have to take a Y circle of a E of G2 is equal to Y is equal to E of G2 and circle of a Y. So this is giving you a Y. So this can be written XY. Similarly, you can just take a EG and comma E of G1, and you have a diamond of x y. This can be written as e.g. Uh, this dot circle is equal to x, and you have a eg of 1, and this is equal to circle of y, and this is nothing but is equal to by again the property of a identity of g. This can be written as a x, and this can be written as a y. So this means this set eg1 are the identity element, is the identity element of a this. So this means we can say that eg1 is the identity element of a g cross g1. Now next we show that this inverse also exists in this case. So if inverses exist there, means we have to some x and y are the element of a g cross g1. So we can say the x inverse y inverse is also the like this. We can say that x y is the element of a g cross g1. Then there exists some x inverse y inverse is also the element of a g cross g1, such that we can say that xy and diamond of this x inverse and y inverse, this should be equal to identity of a g and identity of a g1. If we succeed to prove that this is thing, then we can say that this is identity is inverses exist. So I take a similar form. We just take this form. Now by the definition, this can be written as a x. You have just said that x is the element of a g. If x is the element of a g is a group, then x inverse is also the element of a g, and x inverse is the element of a g. Then this is, by this composition, x inverse is equal to your identity and same as a this x. Also, you can say that you have a y is the element of a g1. This implies that y inverse is also the element of a g1. Then y composition of a y inverse is the same as a, you have a identity of g. This is identity g. Identity of a g1 is the same as a y inverse o. Sorry, this is not o. This one. This is circle. You have a y. So by the binary operation, we define diamond is x inverse. So this is the clearly is giving away eg, and this is giving away by this property eg1. So this can be written into this form. So this means we show that into this. Similarly, if you take a x inverse, y inverse, and then you get a diamond of xy is equal to same as a x inverse of this x, and you have a y inverse circle of a y, and this is again you have a eg, and this is again you have a eg1. That means we can say that clearly identity element is exists here. And if we have to show that if this is clearly satisfied to this form, so this means we both those is exists there, then we can say that if these two are identity, then xy inverse is equal to nothing but is equal to x inverse and y inverse. So we have to just show that composition is equal to identity. So this means inverse of this is nothing but is equal to x inverse and y inverse. So now we have to show that if suppose we have these two groups are g and g1 are abelian, then this direct product is also an abelian group. Suppose g1 and g2 are abelian, and then we have to try to show that this direct product of these two groups is again is an abelian group. So just try this one. We just try to we take x1 y1 x2 y2 are the element of a g cross g1. So we just take a x1 y1, and then we have a diamond is equal to, you have a x2 y2, and then this can be written as a similarly by the definition of this diamond, then x1 x2, and then also we have a y1 circle y2, and now you have just said the x1 and x2 are the element of a g, and then we have a y1 y2 are the element of a g1. If this g is a abelian group, then you can say that you have clearly say that this binary composition of this is the same as a x2 composition of x1. So similarly, this g1 is also abelian. If this g1 is abelian, then we can say that this y1 circle y2 is the same as a y2 circle y1. So this can be written because g and g1 both are we have given is an and abelian groups. So both are abelian groups, means this can be written in the form of this x2, and we have a x1. This can be written in a y2 circle y1. And now this again using the property of a diamond, this can be written as a x2, and we have a y2, and diamond of this is equal to be written in the form of we have a can be written in the form of this x1 and y1. So this means we show that this x1 y1 diamond x2 y2 is the same as a x2 y2, and we have a x1 y1. That means if we have a g1 and g2, g and g1 are the two abelian groups, and then the direct product of these two group is also an abelian. So we prove that this means clearly G cross G1 is a group, and this is if G1 G2 are abelian group, then this product is also an abelian under the operations we have to define into this form. So this is clearly we write using the commutativity condition of a G and commutativity condition of a G1, and then we have to show that G cross G1 is abelian. Okay, now from this we define the definition of a direct product. Let the group G cross G1, we have to show that under the operation we have to define is a group, and this group is called is a direct product of a G1 and G2, and this we have to call is an external direct product. Why is external? We have to just simply take a Cartesian product of this, and so we have to this is a external direct product. Now we take three types of binary operation. One is defined x1 y1 composition x2 y2, and then we have to using the binary operation G and binary operation G1. And now no need of every time I just write of these three operations every time. I just simply clarity I just write in the form of this. This means this is a binary operation of a this G cross G1, and there is a binary operation G, and here is a binary operation of a G2. So similarly, we just not mention how every time is this operations of these three different binary operations. So I just simplicity, I just write a product of this. This means it simply is a component wise multiplication operation is there. X1 x1 x2 y1 y2, and that is nothing but is the element of a G cross G1 by simple way we using as a Cartesian product in the form. Okay, so I just start a very simple example. Let R be a group of real numbers under addition. The Cartesian product of R into itself, this means R2 is nothing but is equal to R square, is a group. You can know that R2 is a group, and this because we just say that under addition. So we take a B binary operation is this, then this is A plus C and B plus D, and then if you can verify, this is clearly A, B, C, D are the some real numbers. So this is satisfy the clearly all the properties we have to just, and in this group we have a 0 0 is the identity, and the inverse of this is equal to minus A minus B are the inverse in this case. So this means clearly this is the very simple example of this. If a real number under addition, this is clearly is a group, and it's take a direct product is nothing but is equal to simply is equal to R square, and you know that R square is again is also is a group under the operation of addition. So this is clearly we can say that. Similarly, we can just say that R3 we can write in the form of a R, and then we can say A, B, C, D plus E, F, and then we have to define in the Citroen way. So with the operation being a component wise addition, this concept can be extended from a direct product of any finite number of a group. So by this we can say simply we can say that we have to take two groups G and G1. We can extend this concept for a finite number of groups we take. If we take a G1, G2, Gn are the finite group, then we can also define this concept can be extended this. So for example, let G1, G2, Gn be finite collection of groups. and now G can be defined as a G1 direct product of a Gn, and that means this is the element of a x1, x2, xn, such as xi is the element of a Gi, I running 1 to n, and then this G under the operation we have to define. So this G is called is the external direct product of a G1, G2, Gn under the component wise operation. So by the component wise operation is like this: x1, x2, xn, y1, y2, yn. Then this is the operation of a G1. This is the operation of a G2. This is the operation of a G3. So this means Gn. So whatever operation of a here is operation is a G1. Here is operation, and here is operation of a this G. Under this, so we have a component wise. We have to addition this defined into this form. So clearly, if we have a under addition, there is addition. Under multiplication G2, and then similarly we using into this way. This can be extended to a direct product of this way. So this is clearly, again you can verify is equal to this is a close, because this all G1, G2, Gn are group. So this is the element of a by the operation is closed G1. This is G2, Gn. So this is nothing but it is the element of a G. G is nothing but is equal to G1, G2, Gn. And now if you take a identity element of this, nothing but is equal to 0, 0, 0, or we have to just say not 0. Under addition is 0, but we have to take a E1, E2 up to En. E1 is the identity of a G1, E2 is the identity of G1. Then we have a x1, x2 up to xn, and that can be written as a E1, x1, E2, x2, and so on, En, xn. And this is nothing but is equal to x1, x2 up to xn by the property of a G1, G2, Gn for identity we have to use it. So this means this is this operation usually is associative. We take a third one and then using the property of this, and also closed, and naturally this is also is a associative, and I just show that the identity also, because E is equal to E1, E2, N is the additive identity. And similarly we can just check x1, x2, xn. So this is x1, x2, xn. Again you have want to just check. You just take a like this. You have a x1, x2 up to xn, and then we have a x1 inverse up to xn inverse. Then this is can be written as a x1, x1 inverse, and so on, xn, xn inverse. And this is nothing but is equal to x1, x1 inverse is equal to because G is a group, x1 is the element of a G, x1 inverse also G, then composition is equal to E1, and this we have a En. So this one you can say that clearly E1, E2, En is the identity of this group G, and if x1, x2, x inverse of this is nothing but is equal to x1 inverse, x2 inverse up to xn inverse are the inverse of this group G. So this means if we have to define for 2, I just show you if a direct product of a 2 groups is again is a group, but we can extend is a finite number of this group G1, G2. Here we have to define the operation is simply is a component wise. We have a x1, y1, x2, y2 in this form, and then we have to clearly write this is again a collection of a group. Now the direct product of n groups I just denoted every time in place of a G. I did a product of a I running 1, 2, and Gi is simply is equal to G1 cross G2 cross and Gn. This product is defined in the same way as before. This I just said that previous slide is equal to this way. If all groups of the same, if we take a G1 is equal to G2, so all are the elements of a G. So this means this instead of a G to the power n, we often write G to the power n, and because of a G cross G is n times. However, G1, G2, Gn are additive groups, so we may use the direct sum notation is there, this form. So I running 1, 2, and G of I, G1, direct sum of G2, and so on. If we have a under binary operation is this form. If we have to write as a simply is a this group is under addition, so we use this notation for into simplifying this group into this form is there. So clearly we have to write in this. Let's very simple example. I just starting from this. Take U5, and then you know that the element of a U5 which are relatively prime to 5, 1, 2, 3, 4, and U12 is we take elements of the relatively prime for this 12. So you have a 1, 5, 7, and 11. If we take a Cartesian product of these two, and now if you have to simply they said one is 1, 1, 5, and then you have 1, 7, then 1, 11. So this is the element of this 1, 5, and these are the elements of this group. Is simply now we have a 2, 1, 2, 5, 2, 7, 2, 11. Then we have to take a 3, 1, 3, 5, 3, 7, 3, 11, 4, 1, 4, 5, 4, 7, 4, 11. Now how we these are the element of this all this thing, but we have to some more elements. If we take a write in this form, if we take a 2 element, I choose this is equal to 2, 7, and we have to take as equal to 3, 11. What is a product of these two? Then you have a 2, 7, and then we take a 3, 11, and then you can say that 2 into 3, and then this is, and then you have a 7 into 11, because these two groups are under multiplication modulo. This first one is a under multiplication modulo 5, and this is under multiplication modulo 12, and that is equal to 6, and then 6 is under multiplication modulo we have to take a this is equal to 1, and then if you have to take a 7 into 11, 77 under modulo you have a 12, and this is 77, then you have a 72, the remainder is equal to 5. So in this case we have a 2, 7, 3 product of a 2, 7 and 3, 11 is equal to 1, 5. For example, I take this is equal to 3, 7, and we have to take a 2, 11. Then what is the element of this is equal to 3 into 2, and then you have 7 into 11. Then again you have to getting this is 1, 5. So corresponding to this also 1, 5. For example, you take a 3, 7 and 4, 11, and then you have a, if we take a 3, 7, and we take a 4, 11. Now you have a 3 into 4, and you have a 7 into 11. 7 into 11 you have under multiplication modulo 12. So this is again you have a clearly is equal to 5. Now this is equal to you have a 3 into 4 is equal to 12. 12 under is equal to modulo this is 2, 5. So in this case you have a getting is equal to 2, 5, and 2, 5 is also here. Now we try to some other we take as for example I take this 3, 5 and 4, 7. So 3, 5, and I take a 4, 7, and in this case you take a 3 into 4 and 5 into 7, and 3, 4 is equal to you have a 12 is equal to 2, and then 5, 7 is equal to 35. 35 means you have a and divided by 12. 35 divided by 12 you just calculate, and then the remainder. So you have a you just take a 11. So this is equal to 211 is also here. So this means you have a you have this clearly is equal to 35, and 35 is divided by 12. Then you have to take a 12. Then remainder is equal to 11. So clearly you have a 2, 11 are there. So this means we take a composition of these. So this if we take some other composition, all are the elements of this is equal to into this form. For example, 4, 5, and 2, 11. You take a 4, 5, and we take a 2, 11. Then you have a 4 into 2, and you have a 5 into 11, and then it is equal to 8. 8 is equal to you have given 3, and this is equal to 55. You have a 48, sorry 7. So 3, 7 is there. So if you take all the compositions are there, then we can say that this is clearly satisfy all the elements are there. This is 1 comma 1 is working as the identity element is there, and now if you want to see this is equal to 1, 5, and 1 into 1 is equal to 1. 5 into 5 is equal to 25. So 1, 5, and then you have to take a 1, 5. If you getting these two elements, so you have to take a 1, 5, and you have a 1, 5 is equal to you have a 1 into 1 is equal to 1. 5, 5 is equal to 25 divided by 4 is equal to 1. So this is 1, 5 is the inverse of each other. And then if you take a 1, 7, and then you have a 1, 7, you have a 1, and 7, 7 is a 49, and then again 1. So this is 1, 7 is also inverted self. and if you take a 1 1 11 is also the inverse of itself. Now we take some elements of this, where 2 and 3 is giving you a 6, so is equal to 1, and then you have a, again you have to take a 2 and 1 into 11 is not, so this means you can find the inverse of a some other element of a in the similar fashion. So 1 1 1 is self inverse, 1 5 1 7 1 11 are the inverse of a each other, and then you just check into this or other element, the elements of this is inverse into this form. So we just take this is the one of the example. I take that u5 and u11 12 into this form. I just take one more example. Consider the group of Z2 cross Z5 consists of element of a, because Z2 you have a 0 and 1, and Z5 you have a 0 1 2 3 4. So this means is equal to 0 0 0 1 0 2 0 3 0 4, and similarly you have a 1, and these are the total elements of a consist of a, this is equal to this form are the element of it. Now if you want to check this is a group or not, by the computer by the table you can also check, because you have to this form. So I just try to let examine the subgroup generated by 1 1 is on this operation of addition. So if you take I just take a 1 1 means you have a 1 into 1 is the same is here. So now 2 times of a 1 1 means we have a 1 1 square, means we can say that 1 1 addition of a 1 1 is equal to 1 1 is equal to you have a 2 2 is equal to you have a 0 and 0 2. So 2 times of this is equal to this. Now 3 times you have a you have again adding this is equal to 1 1, so 1 3, and then again you have a 4 times is equal to adding is equal to 1 1, so 2 is equal to 0, 3 plus is equal to 4, and again adding is equal to 1 5, 1 5 is equal to 0 1 0, and then you have a 6 times you take similarly all the single element. Now you see this 1 1 can generate the whole the elements of a group. You see 1 1 is here, and then you have a 0 0 2 is here, 1 3 is there, 0 4 1 0 0 1, and then you have a 1 2, and then you have 0 3 1 4 and 0 0. So this means you have a 10 elements, 1 2 3 4 5 6 7 8 9, so 10, and then also 1 2 3 4 5 6 7 8 9 9 10 is all are there. So you have a 1 2 3 4, and you have 5 6 7 8 9 10. So this means Z5 Z2 cross Z5 is a generated by this 1 cross 1 comma 1. If it is generated by this, this means clearly this is a cyclic group is there. So this means we can say that this is clearly is a cyclic group of there. Now I just stop today's lecture by this example, and then we continue in the next class also some examples of a direct product where we show that is a isomorphic to some group or not, and then we have to try to prove some properties of a direct product and move later on. So thank you very much for this lecture. We continue next class. Again is a direct product.